Good morning, everybody, and welcome. I'd like to talk about full system simulation and how that can hide or reveal multicore. And exactly what I mean by that, I hope will become obvious when I talk here. First, a general disclaimer. Opinions expressed are solely my own and should not be attributed to Intel, where I currently work. Now, way back in the 1990s, I attended a talk on parallel programming and multiprocessors. Now, back then you had to call multi-core, multiprocessor to get a research grant because multi-core was not the term you used. But fundamentally, the problems were the same, in essence. Now, this gentleman, whose name I've unfortunately forgotten, he had spent a lot of time analyzing this problem. How do we program these beasts? And he came to a fairly short summary or conclusion of this, and this was his first conclusion. Thinking parallel is difficult. Okay, right? So, being a scientist, he didn't stop there. He continued thinking. And he came to his second conclusion. Thinking sequential is difficult. Now, facing the facts, he drew his final conclusion. Thinking is difficult. Right? Now, of course, this wasn't all completely serious, but as in all good jokes, there is some truth in it. So, if the problem is that thinking is difficult, then I would like to suggest a solution to you. Why don't you reduce the need for thinking by using a deterministic full system simulator? Okay. So what is a full system simulator? Some of you may be very well aware, but I'd like to give you an overview anyway. So, the way we describe full system simulation is that you run all the software unmodified at near hardware speed on the simulator, right? And then you replace all the hardware with models. They mimic the function exactly. So the software thinks it's actually running a hardware, but they try to cheat with everything else. So most importantly, it simplifies timing. So it doesn't take 32 clock cycles or half a clock cycle to run an instruction. It takes something simple like 1 clock cycle, right? Now, the purpose of a simulator is to be able to somehow understand your system. So, of course, you add inspection and control, right? So, one of the most important features is that you can stop time. And this means that everything stops, right? Everything stops. There's nothing running. So you can stop, and then you can do arbitrary inspection and figure out what is the state of the system right now. So if you think you can have your PC, you can have your television set or your smartphone, or even a system, all three that's communicating with each other. And you replace the hardware with models in the simulator, but the software that's inside, you use that unmodified. So, the exact binary that you compiled for the real thing. So you can boot Windows on a full system simulator, right? You can do networking if you want to. Now, just to be clear, there are other types of system simulation, and it's becoming more and more popular now with the advent of sort of portable things where you need to think about other things than actually getting the software right. You want to check the power, you want to understand the performance of the system. However, you should really think about keeping these things separate. So, just an example, this is a very simple power model of my television set at home, right? If it's turned off, it consumes 0.35 watts. Okay, if I turn it on, it consumes 38 watts. Now, inside that television set, there's an embedded processor. It has a really crappy web browser, but from a power perspective, I don't care about the instructions running there, right? This model is enough for a lot of users to understand the power consumption of it. So when you model, you should be thinking that models, they're built from a perspective, right? So you have the system here, and you may want to build a power model, and that's looking at the system from one angle, or you may want to build a performance model, that's another angle of it. Or you may want to build a functional model, what has been usually referred to as full system simulation, which models the function, and that includes running the software unmodified. Now, what you usually do not want to do is build a model that models the function, the performance, and the power at the same time, because that turns out to be a very, very slow model. And what happens is that users are impatient, so they're really not interested in using that. As part of a company that does tools, I've often encountered this when you come to customers. They say, well, oh, it's great you can do the function on this, I can write my software. How about you fix so that it also models the cache and the latencies of everything? Because that's cheaper for us, right? We get two models in one. Well, you get one model instead of two, but it's going to be so slow that it's going to be unusable for the guys that only want to debug the function. So that's something to keep in mind. And for the rest of this talk, I'll focus on the functional model. And I think we'll hear more about the performance aspect of a system in a later talk. Right, so I said that we wanted a deterministic simulator. So now what's the problem with indeterminism? Well, you've probably encountered this, but basically, right, if you run it repeated times, it yields different results, right? And you've got no control over which one happens. So here's a very simple example of a sort of hypothetical system where a discrete event system with the events A, B, and C. Now you start off, and then A, B, and C happens, but you don't know in which order. So A, B, and C can happen, and the result is okay, and CBA happens, and the result is an error. Now, some of you, I think, have encountered that you've written this very nice multi-threaded program, and you run it, and it works, and then you show it to your colleague, and it crashes. Right? So, typical example of indeterminism. So, what do we do about this? Well, what I'm proposing is to use a deterministic full system simulator. Now, that basically means that for each run, all the events that happen in the simulator, instructions, interrupts, device actions, they occur in the same order, at the same virtual time. Any input to this can be recorded and replayed, and the simulator features in themselves, they do not affect the simulator if you inspect something. So if you write a script that checks the state of the simulator every now and then, that script will not affect what is being simulated. Even if you do reverse execution, the proper property that the simulator runs backwards, that does not affect the simulation. If you run backwards and then you run forwards again, you will end up in exactly the same place. Now, one property of this, if you write the simulator the right way, is that any software that you run on this, remember we had this sort of the same software that ran on the real system is now running on the simulator. Any software will become deterministic on the simulator. So this is something that we've encountered multiple times, that you come to a customer and you say, oh, we've got this deterministic simulator. And then the customer says, well, we really don't care about determinism because our software or our system is indeterministic. And these are smart people, right? But still they make the fatal error, fatal misconclusion that, well, the system they have might be indeterministic, but if you remove the hardware and replace it with deterministic models, it will become deterministic. So they will have a deterministic system when they run on the simulator. So now we've got this wonderful tool, deterministic simulator. What can it be used for? What is it good for? And I'd like to show you a couple of examples of what we've done, what actually has happened when Simics has been applied at different users. So these are sort of real problems with real solutions. So the first example I'd like to show you, case A, the rare file system corruption. It was this following scenario. Okay, you had company A who had an embedded operating system with a distributed file system developed by company B. So company A was sitting there with this system. They had this file system. They bought it from somewhere. They only had the binaries, right? They didn't develop this, so they wouldn't really know how to fix the bug if there was a bug. But there was a bug in it, right? So the problem was the file system got corrupted. The behavior was intermittent, and they've been chasing this for months. I don't know exactly how many. I think it was 3 months or more. Okay. And of course, this was a big problem for them, right? So finally, they said, all right, we want to find this problem. We can't have a file system that gets corrupted every now and then. So they moved their entire system, so which was multiple computers talking to each other over networking, Ethernet, right? They moved it to the full system simulator. They ran the system and the corruption occurred. And now, because the simulation was deterministic, they could pinpoint exactly where it happened. So they could stop the simulation, see if the disks were corrupted. They could look at all the disks on the different computer at once without affecting the system and see, okay, it's okay, let's move on. And narrow down the interval to actually the exact instruction where here's where it's going wrong. But not only that, once they've done that, they can send it to company B and say, look, here's exactly what you do to end up in the problem, and here where it goes wrong. Please fix it. And I don't have the exact number of the time it took for them to do that, but that was in the order of a week or a couple of weeks, right? So, next case, the maximal configuration test. Now, you have this embedded system which can be configured with multiple racks, each consisted of multiple heterogeneous boards, each consisting of multi-core processors, right? Now, if you multiply that out, it becomes a big system. We're talking hundreds of cores, okay? Now, the problem is, okay, what if I build a maximum configuration system? Will it boot the software I've done, okay? And will it work when I get a new version of the software, well, which is being continuously developed, right? Well, the solution is, okay, you model the entire system in a full system simulator, right? And then you develop an automated test suite that does the boot and check if all the nodes are saying, I'm okay, I've booted, I'm working. So you think about this and say, wait a minute, this can't work. We're talking hundreds of processors here, and maybe you're running it on a server that has 10 or 20 processors, cores, sorry. 10 or 20 cores. How come that you can run at near hardware speed, which I said originally? Well, the reason is that, well, actually sort of it's a little bit what Trevor talked about, right? When these kind of systems boot, they don't do that much. It's actually fairly sequential in many aspects. So if you're smart when you build a simulator, you can actually run a system with hundreds of processors on a simulator host, which also only has a couple of processors, and get decent speed out of it. Okay. Now you might argue, aha, well, you really don't need a deterministic simulator to do this. No, that's true. As long as the test passes, it's okay. You could have an indeterministic simulator and just say, well, the system booted, I'm fine. However, if there is an error, you really want it to be deterministic so that you can do sort of a bisection and find out where is it going wrong when you rerun the boot. Case C, switching to a detailed multi-core model. So now I'm going to cheat and say I wouldn't talk about performance. I'm going to talk a little bit about performance here. Here you had a semiconductor manufacturer that had a detailed model of critical parts of the multi-core system. So they had the processors and the central devices, but they didn't model everything. Right? And then they had, okay, we actually want to use this to do some benchmarking. The detailed model actually was cycle accurate. So you could actually tell how many cycles it would consume to run a particular program. The problem was that the kind of benchmarks that they had access to typically required a system to be booted first. And to boot that on a detailed model, it would require weeks of wall clock time to do. So that wasn't realistic. So what did they do? Well, they booted the system on a full system simulator which has a simple model of the processor, but it's complete, right? Modeled the whole system, and they positioned the workload, and then they took the state of this simple, essentially multi-core model, moved that to the detailed model, and hooked in the detailed model into the simulation, kept the other peripheral parts that weren't used anymore, or not that much at least, and run their application. So what do you do about warming up the caches? That's a problem, right? When you're at the start of the application run, the caches are essentially empty. So you need to warm them. In their case, their workloads had fairly small working sets, so they could get away with it. But we'll hear more about how you can do that even better in some other talks. And finally, here is case D. Now, this is the one I know most about, because this is about Simics itself. Now, Simics itself is a program, an application that runs on a computer like any other program, right? Now, we wanted to improve the speed when you simulated a multi-core system. So in Simics 5, you can do that, the latest version of Simics, by simulating each core in parallel. So you've got a thread that handles each of the cores that are in your configuration that you're currently simulating. Now, when you do that, it becomes indeterministic. Unless you put in, well, you can do it deterministic, but that's even more work and it will slow it down. So we wanted to have a mode that was as fast as possible, and that was indeterministic. The problem now becomes, okay, how do we test this? Now we run into this thing that we've got this program that can behave differently each time we run it, and it did, right? And there were fairly tricky bugs to find. Now, how did we deal with that? Well, the solution was to run Simics on Simics, right? So you have the indeterministic Simics, which is an application running on an operating system, and that operating system runs on the full system simulator, which is a deterministic Simics. Now, all of a sudden, okay, now you've got a deterministic simulation. The same thing will happen each time. Well, that's bad, right? We want to see all those different paths that I talked about before. We want to be able to actually get to all, or at least most of them. How do we do that now? Well, it turns out it's not really that hard. What you can do is, in the outer Simics, the deterministic Simics, you can change the interleaving of how instructions are simulated. And that is enough to provoke the different paths that multi-threaded programs take. So here I'm showing a very simple example, right? There's 3 processors, P1, P2, P3, and they can either run 1 instruction each, or you can have P1 run 2 instructions, and then you simulate 2 instructions of P2, and then you simulate 2 instructions of P3. And if you think about it, that is how a multi-threaded program actually can behave, or how what creates the different paths in a multi-threaded program. So you change the interleaving, and you will hit the error case. Now, there is, of course, a slight problem here. There are very many interleavings, so like really, really many. They will not fit on a PowerPoint slide even. So what you do, or what we did, it turned out that you could do something fairly simple, and it worked. So for all the cases we tried, were not too many, because you only use this tool when you've discovered that there is a problem that you actually want, that is hard, right? The easy problems you can solve with a standard debugger and you're done. But when you start hitting a problem that you see, okay, this problem moves around. Okay, I really don't know where it is. Then what you do, or then what we did, was the following. Okay, you create a test that has a pass-fail criteria, right? Easy enough, okay. And that test has to sort of, you want that test to cover the problem you're seeing, right? And then what you do is you set up a batch run. And what you repeat is, in deterministic Simics, you randomly select how many instructions you want to run, which is, we usually refer that to as a quantum. We chose to randomly just do something between 10 and 100,000. This is a research field in its own. How do you select that to become efficient? We didn't have to care about that, because we could get away with just doing random, run the test. If the test failed, we were done. That meant that, okay, we've found an interleaving that triggers the problem. Then we can use standard debugging. We now have a single path that we just go back and forth along until we found exactly where the problem was. And in the cases we tried, it wasn't enough to run 100 iterations, or in that order, which in our case completed overnight. So you set up the batch run, you go home, and the next morning the program told you, here's how you do to repeat the error. And you'd know that, okay, if I do it exactly like this, the error will repeat itself. It will not vanish, right? Even if I start instrumenting it and try to narrow down exactly where it happened. Because sometimes these tests, most of them were fairly short, but even if they were long, you knew that you now could narrow down to exactly where it occurred. So in summary, a deterministic full system simulator is an important tool to develop multi-core systems. It provides access even if there is no hardware. It simplifies finding, reproducing, and tracking down bugs. And most importantly, it reduces the amount of thinking, the difficult stuff. And with that, I'd like to conclude, and thank you for listening.
So once more, we have microphones for questions, so raise your hand. I have a question for you.
Yes.
Is it really, really deterministic? Hand on the Bible?
Hand on the Bible, yes, it's really, really deterministic. And yes, there's really, really bugs, right? But what you can say is that it is deterministic to the level that the bugs that are in the simulator are so few that as a user you can use it and think of it as deterministic. Now, when you say really, really deterministic, I think that the common mistake you would do as a user is not discovering, or not mistake, the common case is not that you would discover a bug in the simulator, because if you design it from the start being deterministic, it's really not that hard to maintain that. But, of course, there are modes in the simulators which is not deterministic. So, for instance, the mode I just mentioned, okay, I want to run max performance, I'll actually switch to a mode which is indeterministic. Well, then it won't be deterministic anymore. Or, well, in this simulation, I'm actually going to accept to communicate with the real world, which you can do. So you can have a computer simulated and it's got a networking connection and that connects out into the real internet. Now, all of a sudden, you've got input coming in from the real world, and that is not deterministic. And then you have to make sure that I turn on recording that input, so the next time I run, I'm running exactly the same thing. So that is the more likely problem that you will run into. Or, okay, I'm running my simulation, okay, I boot the system and then I type this command. Now, typing commands is again input. We record it, so if you just turn on the recording and next time you make sure that that is the same input you use, then it will be deterministic.
So what kind of slowdowns do you have? Because if you're going to get test coverage, you need good efficiency to hit all the bugs, not just, you know, it's going to take forever to find that magic bug.
Right. Okay. Slowdown is it depends is the answer as usual. And it depends very, very much, right? It depends on what architecture you're simulating, because some architectures you can actually use backends which are faster. It depends on the size of the system. As I mentioned, okay, you can have hundreds of processors.
Four cores. 4 cores, ballpark, 10 times, 100 times.
No, 10 times or less, I would say.
Okay, so
yeah.
It's very decent.
Alexandra Jimboran from Uppsala University. So you were mentioning that in order to verify the indeterministic mode of the simulator, yes, you actually tested by generating a lot of tests for the deterministic full system simulation, right?
Yeah.
How do you generate good test cases?
So, yeah, good question. So we chose not to sort of, we didn't have a test strategy saying, okay, we're going to use Simics to test the indeterministic version. We tested it in the indeterministic system in a more traditional way. You ran tests on it. But so it was first when we discovered that here is a problem that's moving around. Then we sort of brought up the big gun. Then when we say, okay, let's write a test for what we think this problem has to do with. Then do the batch process, as I said. Then because it ran overnight, right? So if you had easy bugs, then you use traditional testing. So I hope that answered the question.
Is your product available as beta, or how far away is it from commercial use?
It's been commercial since 1998. We've modeled most of the major architectures as we got customers. We started out with Spark. We did x86, PowerPC, ARM, MIPS. I'm starting to forget, and more. So yes, it's commercially available. And what usually happens is that when a customer wants to use this, they're usually interested in modeling their exact system, right? So some customers have large embedded systems, so we talk to them and say, okay, what process do you have? Because that's where you usually start, okay? And we usually have most of them pre-made model or already in stock, or And this continuously evolves, of course. Architectures come and go, but the simulation infrastructure stays the same.
Initially, you had a great product name for this. It was called Hindsight, right?
Yeah.
You still use that?
We do, but
and this is sort of interesting. He mentioned that just briefly. You can actually execute backwards.
Yeah.
Right. So I've seen systems unbooting on their simulator. So devices go away, right? Because you execute backwards. So it's amazing. Oh. So a question up there.
As you mentioned, you're running the full application.
Yes.
On top of it, on top of your simulation.
Yeah.
Can you describe kind of clear line between the emulation and this platform? Because the emulation is pretending to show the hardware behavior during the time, and in the simulation you're jumping between the times, and you're running this exact application time by time. You're not jumping, for example, during the time that you're actually running the application. So you can clarify between the emulation and the simulation platform that you have?
Okay, I'll describe the way I've interpreted the words emulation and simulation. Now, in emulation, what you're striving for is just to run something. You're not striving for to inspect it in any way. So you can't stop time in sort of an emulator. Now, some people use emulators in a different way, but this is how I define it, right? So an emulator just wants to run the program. It does not want to inspect it. So you can't stop it. You can't say, what's the value of register X inside this machine? Or maybe some coarse-grained statistics. How many times have I accessed this device? I'm not sure if I answered your question, but that's Simics is a simulator. A full system simulation is about being able to inspect what you're running, not only to run it. So did that answer the question? We can take it offline. I'll be at the table with my name on it.
Since you are so modest and you don't do much marketing, we should probably stress that you support other processors than Intel processors as well, right?
Yeah, no, sure. Yes. As I said, this product has been around since 1998. We were acquired 5 years ago, and of course Intel as a company is very interested that we have Intel models, but we still have all the other models too. So we build heterogeneous systems with all kind of processors and devices inside them.
Okay, great, thanks.
Okay.